Drones are increasingly being used in a broad range of applications, from building and construction, where they're used for 3D modeling of sites, to inspection, to agriculture, and even security. By eliminating the need for expensive equipment and infrastructure, they've made it easier for vloggers and hobbyists to create professional-looking content, and there are even plans to use drones for creating habitats on other planets such as Mars. In light of these developments, the project was focused on designing path planning and obstacle avoidance algorithms. Therefore, to begin with, we looked into using a neural network like TensorFlow. In layman terms, a neural network, much like the neurons in your brain, is a multi-layered Markov model which works by the activation of layers, which depends on input parameters, to produce a desired result. Thus, we can teach the drone to identify obstacles and then perform the relevant maneuvers to avoid them. We also looked at existing algorithms such as potential field, which works by the principle of virtual forces, where the drone is attracted towards a goal and repelled away from any obstacles, with the final path being the resultant of these virtual forces. We used ROS in conjunction with Gazebo, which is a physics software simulator. The test drone would use a downward-facing camera providing distance measurements for the optical flow sensor using infrared technology. We then turned our eyes to an industry-widely adopted technique, PID.
In contrast to using feed-forward, which requires knowledge of process parameters, PID is a form of feedback control which can be implemented without a precise system model. This form of control is the superposition of proportional, derivative, and integral actions. The proportional term acts on the present value of the error between the desired and current states. The integral term considers the time history of the error and guarantees convergence to the desired set point. Lastly, derivative action can be interpreted as a prediction of future errors based on linear extrapolation. Due to its effectiveness and relative simplicity, over 90% of industrial applications use some form of PID control, ranging from pH monitoring to automobile cruise control. One of the critical aspects when designing a PID controller is tuning the gains to achieve optimal performance. Based on the actual task, we split the flight into different segments. In the first stage, takeoff, gains were optimized to maintain constant X and Y positions while having a vertical velocity of 0.4 meters per second. This was followed by a hover segment, where the gains were designed to keep an altitude of 1.5 meters for 2 seconds. Next, the drone cruised for 6 meters at a speed of 0.5 meters per second and a constant height of 1.5 meters above the local ground, thus avoiding the obstacle. After this, the drone hovered above the landing point for 2 seconds. Finally, landing was divided into 2 stages, both optimized to maintain constant X and Y positions. The latter one, being triggered at an altitude of 0.4 meters, had a lower descent velocity so as to ensure a safe touchdown. Nevertheless, the main reason for dividing flight into stages was that, for this highly coupled nonlinear system, different stages have different dynamics. This must be reflected in the choice of PID gains.
Tuning a PID can be thought of as being more of an art than a science, especially when there are model uncertainties. There exist different tuning methods, such as trial and error or LQR. Among these, we decided to use the heuristic-Ziegler-Nichols method as a guideline. This method consists in increasing the proportional gain until the system has stable and consistent oscillations. This ultimate gain and the period of oscillation were used to tune the PID gains. Generally, this yields aggressive gains and overshoot, thus making it imperative to adjust the gains for each stage. Real physical systems and sensors are imperfect and subject to measurement noise. This especially affects derivative action, as it generally involves using numerical differentiation, which amplifies noise. This problem was circumvented by using velocity data from the IMU. This velocity is obtained directly from the sensor data and has less noise. Furthermore, for safety purposes, a form of saturation was introduced to prevent velocity commands exceeding 0.5 meters per second in any direction.
Starting with a simple ramp, the drone first takes off smooth and nicely from the ground and hovers at the desired altitude for a few seconds exactly as we have programmed it. The drone then cruises straight towards the ramp at constant altitude. Once it approaches the ramp, the drone is very sensitive in detecting the ramp and increases its altitude almost immediately. It then steadily climbs over the ramp. In addition to a ramp, we also test the drone on several other obstacles to ensure that the drone will perform well in a variety of environments. In actual experiments, we test the drone twice, having a simple ramp as an obstacle. Test using camera, the drone took off and hovered nicely. For some reason, the drone lost some altitude during cruise. Detection of the ramp was pretty responsive, as expected, although the drone experienced large overshoot as it descended. In the second test using optical flow, the drone performed relatively well from start up to climbing the ramp. After that, errors seemed to build up and the drone did not descend properly and went straight to hit the nets in the end. This then leads us to discussion of the reality gap.
Whilst the Gazebo model provides a satisfactory representation of the system, a reality gap exists. Real-world effects on the system that have not been accounted for. A primary reason behind this reality gap includes magnetic and optical effects. The presence of magnetic fields, created by something as simple as a smartphone, have adverse effects on the Pixorgan IMU used in the navigation system. The IMU data can also be affected by mechanical vibrations, as well as by imperfect mounting of the unit. Furthermore, unwanted reflections in the lab can distort the images received by the optical flow sensor. Aerodynamic models took no account for the downwash created by the propellers, or for the boundary layer created over the propeller surface. Structurally, the drone was assumed to be perfectly rigid, thus ignoring aeroelastic effects. Another factor was the use of the optical flow sensor. In order to minimise the cost function used to determine performance, the velocity of the drone in the x direction was increased. This increase in velocity caused the quality of the position estimate to deteriorate, resulting in an error accumulation which led the drone to crash into the net.
In summary, it is possible to devise a precise and complex tracking algorithm in a simulation. However, when implemented in a real environment, a simple and robust solution designed with available hardware in mind can prove to be superior. For example, a prototype for a ramp detection algorithm was envisaged to slow the drone, thus improving responsiveness to obstacle detection and minimizing overshoot. The use of filters was investigated to mitigate noise, but the associated loss in responsiveness was deemed too severe.